Hello, my name is Juliana Noronha, and this is my final project presentation for Data 675, where I worked on modeling crash data in San Francisco. If you saw my previous presentation, some of these slides will look familiar, but my goal is to focus this presentation on as much of the new content and findings as possible. I want to cover what this project is, how it was built, and what the outcomes were. For the what, I built an exposure-normalized crash rate for San Francisco intersections alongside two crash severity classifiers. I did this by dividing crash counts by measured traffic volume to produce a danger rate, and separately by training machine learning models on crash condition features to predict how severe a crash would be when it did occur. The outputs are an interactive map that ranks intersections by crashes per 1,000 daily vehicles, and a champion predictive model whose findings can inform real infrastructure and policy decisions. The core problem that I set out to solve is that raw crash counts conflate two very different things. An intersection that records many crashes may simply be busy, or it may be genuinely dangerous because of fixable features like poor lighting, confusing road markings, bad signage, or geometry that encourages speeding. Those signals are invisible in raw count map because they're drowned out by the total volume of that intersection. My project addresses this from two angles. First, the exposure normalization that I talked about previously, dividing crash counts by traffic volume to identify where crashes are unexpectedly frequent relative to the traffic passing through. And second is that severity prediction, given that a crash did occur, what conditions predict whether it will be serious? These are complementary questions, and together they give a more complete picture of the street danger than raw counts alone, in my opinion. The primary data set I'm working off of is the San Francisco traffic crashes resulting in injury data set, which is maintained by city agencies. It contains over 65,000 crash records and 58 columns spanning from 2005 to the present. I restricted the analysis to 2014 through 2022 to align with the traffic volume dataset, which I'll talk about next. There's a ton of fields in this data set, which include precise coordinates, injury counts, party types, road surface, lighting conditions, collision type, the movement of each party before the crash. It's a very good data set. Some data quality issues worth noting is that 3% of the records had a positive longitude, which would place those crashes in Central Asia rather than San Francisco. So those had to be corrected before plotting. Also, the control device field, which communicates whether the traffic lights or signs were functional at the intersection, is missing for about a third of the records and unfortunately couldn't be used as a predictor. The secondary dataset is the SFMTA intersection traffic counts dataset, which has about 1,200 intersection records across 126 columns covering 2014 to 2022. This is the traffic volume denominator that makes the exposure normalization possible. So this data set identifies locations by street name rather than coordinates, so these had to be geocoded. Additionally, after joining and filtering for quality, only 700 of the original 1,200 intersections remained usable. And additionally, there was this composite metric in the dataset called volume ADT, which would be a very ideal denominator, but it was 97% null. And so I ended up constructing a proxy by summing all of the approach volumes from all of the different time periods that were recorded in the dataset. I want to cover some of the EDA that I did. So this heat map shows crash frequency broken down by the types of parties involved. You can see that driver versus driver dominates at over 9,000 crashes, which is expected since most road users are drivers, but the more interesting ones are driver versus pedestrian and driver versus cyclist, since I think these are likely to result in injury as well. They're also the most vulnerable road users. And the implications are very different for a driver versus a driver versus pedestrian or bicyclist. These 4 bar charts give a snapshot of the distribution of crashes across key categorical variables. So looking at collision severity, complaint of pain is by far the most common outcome, with visible injury and severe injury considerably less frequent, and fatal crashes are pretty rare, which is going to be pretty important when we discuss class imbalance in the models. The road surface chart shows that the vast majority of crashes occur on dry roads, which seems counterintuitive, but we'll cover this phenomenon later in the presentation. Same with most crashes occurring in the daylight. The collision type chart shows that broadsides and vehicle pedestrian crashes are the most common types of crashes, followed by rear end and sideswipe. So I want to get into the mechanics of how I connected the 2 data sets and the challenges that ultimately shaped the rest of the project and the direction I went in. So my join keys were intersection ID and date. Initially I joined on exact date, which is ideal, but there were so few dates covered by the traffic volume dataset that this reduced the row count to just 500 crash rows, which is not enough for predictive modeling. So then I joined on time of day plus day of the week plus month plus year. So not on specific day, but on day of the week, essentially, constrained within the same month and year, which expanded it to 1,000 rows. And finally, I tried joining on day of the week and time of day, which produced around 8,000 rows. Methodologically, this is not the most sound. Of course, exact date is really the best way to go about it, but there just wasn't enough data volume. So the resulting granularity of this data set was 1 row per unique combination of time of day and day of the week and intersection. You can also see here just how few intersections the traffic volume dataset had compared to the crash data, which basically covered the entire city. This is a real limitation of my analysis, and I'll acknowledge that in the findings. Additionally, when I was trying to build the predictive model for the exposure normalized crash rate, I wanted to prevent data leakage about the crash itself. So I couldn't use any information about the crash because I'm trying to predict whether an intersection is more likely to have crashes or not. And if I include things like number of people injured or parties involved, etc., that leaks the fact that a crash happened at that intersection. So the data set could only contain information about the intersection itself in order to predict which structural features contribute to crashes. And this significantly reduced the number of usable columns for modeling. And ultimately, all of this information combined led me to the decision to not model the exposure normalized crash rate and just to create a map from that. This slide puts both maps side by side to make the geographic comparison concrete. The left map is showing the raw crash counts densely concentrated in downtown and along major corridors. The right map is showing the exposure normalized crash rate, which is much sparser due to the data availability issues I was discussing earlier. But you can clearly see that there are some very different intersections that emerge as being dangerous given the amount of vehicles that pass through those intersections. I also wanted to compare my exposure normalized map on the left with the SF Vision Zero High Injury Network on the right, which is a map that the city publishes to show which are the streets you're the most likely to get injured on. And I also included the raw crash count map filtered to intersections with more than 5 crashes. So what's notable is that the Vision Zero network map overlaps much more closely with the raw crash count map than with the exposure normalized one, which is sort of what you would expect. If Vision Zero is built from raw counts, it's going to prioritize the same high volume corridors than the raw count map highlights. And so I really do feel like my exposure normalized map is surfacing a different set of locations. Before I go into the models, I want to talk about the pivot away from modeling the exposure normalized crash rate one last time, which was really driven by all the data quality issues discussed earlier. The volume of data after joining was too small, the join strategy was becoming tenuous, and there weren't enough intersection level predictor variables to build a meaningful model. I did try to build the model anyway, and the models were not very good. We have a random forest F1 of 0.27. I also tried a gradient boosting model, and that had a negative 0.3 r squared. So this is where I decided to predict crash severity given a crash occurred, which allowed me to use the full crash data set and all the information about the crash and parties involved. And so for this, I built two models, which I'll talk about right now. The first model is a logistic regression predicting whether a crash results in a severe outcome, which I'm defining as fatal or severe injury, versus all other crashes, which is complaint of pain and other visible. There's a significant class imbalance with only 9% of crashes being defined as severe. So I added class weight equals balanced during the modeling phase, and it performed pretty well. The model achieved a macro F1 of 0.52 and an AUC of 0.7. Raw accuracy doesn't beat the majority class baseline because predicting non-severe would just all the time would be right 91% of the time. But of course, that's the wrong metric for imbalanced classification. And so the AUC of 0.7 means that the model is correctly ranking a randomly selected severe crash is more likely to be severe than a randomly selected non-severe crash 70% of the time. And the precision recall curve shows an average precision of 0.19 against a baseline of 0.09, confirming that the model is doing more than twice as well as chance. At the default threshold of 0.5, recall is 0.63, meaning the model catches nearly 2/3 of severe crashes. So here are the features that are most associated with severe crashes. Of the ones with large positive correlations with severe crash are parked vehicles. So essentially you have one vehicle that's not evading a crash, and so these do end up leading to more severe outcomes. And we also have merging or getting run off the road. And so these are obviously high speed situations and they have less visibility. So these are more likely to end up with the severe outcomes. Some interesting negative predictors were icy or snowy roads and reduced roadway width. It sounds counterintuitive, but it's actually well supported by what's called the behavioral adaptation hypothesis in traffic safety research, which I learned about because of this project. So drivers slow down and drive more carefully in visibly poor conditions, and the crashes that do occur tend to happen at lower speeds and produce less severe outcomes. And so the same is true for reduced roadway width because narrow roads make drivers cautious, which reduces impact speed when a crash does occur. The second model is a random forest multi-class classifier to predict severity across all 4 of the categories. I initially built a version of this model that had latitude and longitude as features, but those ended up ranking as the top 2 most important features by a wide margin, which sort of goes back to the motivating question of this whole project, which is that it really does seem like neighborhood or location really affects crashes. But I don't want to look at crashes in this, or at location in this case, I just want to look at crash conditions. So I ended up retraining without coordinates, and the macro F1 difference was only 0.1012. So that made me confident that removing it was going to be okay. So the confusion matrix here tells the story of where this model succeeds and where it fails. It does okay on the majority class, which is complaint of pain, with an F1 of 0.74, but it struggles significantly on severe and fatal. The fatal class is basically invisible in the confusion matrix because it's less than 1% of the data, and so even though we specified class balancing during the modeling stage, doesn't seem like that was enough to fix the class imbalances. So what features are important here? When coordinates are removed, the most important features become crash circumstance and time of day. So mid-block crashes occurring away from the intersections are associated with more severe patterns, and it's possible that mid-block crashes are happening at higher speed and thus have more severe outcomes. The afternoon 2 to 6 p.m. window is the second most important feature, which reflects high traffic density, and it could have to do with the low sun angle in the sky. One thing that's notable is that the feature importances are pretty flat, like they all look very similar. This could suggest that crash severity is really very multi-causal with no single dominant driver, but can also be an artifact of this model being weak and not very good at predicting the different classes. In this case, I think both are partly true. This comparison table shows the logistic regression outperforming the random forest on every metric. So it has a stronger macro F1, higher weighted F1, the AUC that doesn't apply to the multi-class model is good, and there was no geographic leakage. It wasn't even a concern in the logistic regression. So additionally, logistic regressions are highly interpretable models. They're easier to understand and communicate about. So for that reason, I think logistic regression ends up being the champion model here. So pulling everything together from the danger map, we had 0 overlap between the top 10 raw count intersections and the top 10 normalized crash rate intersections, which really validates the original premise of this project. From the logistic regression, we learned that parked vehicle crashes are disproportionately severe, and adverse road conditions actually make people drive more safely. And from the random forest model, we learned that mid-crash location is a strong predictor of severity and also afternoon peak. But we also learned in this case that maybe random forest wasn't the best model. 3 lessons that came specifically from the modeling work in this project. Sometimes you really just need more data. So the fatal class being less than 1% of the data set meant the model couldn't learn to predict it reliably regardless of what technique I applied. Nothing really substitutes having enough real examples of the thing you care most about, especially with such a high dimensional data set with 50 different features. That constraint also meant that I couldn't confidently apply SMOTE, because with so few real fatal cases, I think the synthetic interpolation would have been building on a very shaky foundation. The second is that sometimes a well-motivated question isn't enough. I thought the exposure normalized crash rate was the more interesting question, but I just didn't have the data to support such an analysis. I think that doing this again with the Google Maps API could be a really interesting avenue, since that has much higher volume of traffic volume data. Third is that modeling failure is also a finding. The exposure normalized rate models that I originally wanted to build really just reflected, not working really just reflected all of the structural constraints in the data, and accepting that the available data that I had wouldn't support such a model led me to a much cleaner direction and produce results that I can feel confident standing behind. So knowing when to pivot is part of the work as well. Here are all of my references. Thank you so much for your time, and I'm happy to take any questions.